Okay, hello everyone, and welcome to this week's Topos Institute Colloquium. This week, I'm very happy to introduce Shaowei Lin, who's going to be speaking on proofs as programs. So whenever you're ready, Shaowei.
Okay, thank you, Tim. So just want to thank everyone for listening in, and I want to thank Brandon and David for giving me a chance to talk in this colloquium. And so far, the talks in the colloquium have been pretty amazing. So I'm really honored to be given a chance to talk here. Just want to give a little bit of disclaimer. I'm not really a person working in category theory. My main research is actually in statistical learning theory, but I wanted to share a little bit of what I'm doing in the area of program synthesis. So a bit about my background, because I'm new to this community. I'm a mathematician pretending to be a statistician and a computer scientist. So my goal as a mathematician is actually to design and write open protocols for decentralized embodied intelligence. I will talk a little bit about what that means later. My own personal interests, there are three main interests. I'm interested in the statistical learning theory for spiking networks. That's my main focus. I do quite a bit of work also in dependent type theory for machine reasoning. And one of my side projects is looking at quantum path integrals and motivic information theory. So my history is that I did my PhD at Berkeley with Bernd Sternfels. Actually, my PhD was in algebraic statistics. I was looking at singularities in statistical models. And then after that, I took part in a DARPA project that looked at math challenges in deep learning. And I went back to Singapore after that, where I worked quite in a lot of applied projects in this organization called A-STAR and in a program called the Urban Systems Initiative, where we look at smart city applications. And then I was an assistant professor at SUTD, where we had a brain lab that looked at theoretical questions in AI. And now I'm actually in the middle of an international move. So, and also forcing myself to take a sabbatical to work on different projects. But I'm really happy to be able to give this talk and share a little bit of what I've been working on. So when I was in Singapore, we actually looked at smart cities. And one of the models that I really like was thinking about sensor networks and deep learning and all these other tools for machine learning, for AI, as a kind of nervous system for the city. So in the same way that a human body has sensors on our skin, in our eyes, in our ears, we actually have sensors all around the city. And as the sensors send their information to the back end, where we have deep neural networks, it's almost as though that's the brain with neurons computing and so on. So working in that kind of an environment, thinking like this, gave me a lot of questions about program synthesis, which I kind of share. I want to share about this because I saw John Baez give a talk about this nervous system idea, and I think this is a really good way to think about things. So some of the applied projects that I've worked on, I've looked at sensor platforms for smart cities. I've looked at urban planning, where we look at microclimatic models, environmental monitoring, noise pollution, structural health monitoring, where we look at faults on port cranes, infrastructural maintenance on roads, public cleanliness, high-tech farming, elderly healthcare, and more recently, power grid security. So I've been involved in a lot of different applied problems. And it's really interesting to be in these projects as a mathematician, trying to figure out what the real problem is, trying to figure out what's the best way to model this. And so a lot of the ideas that I'm sharing today, it's coming out from the years of really thinking about issues in these areas. So instead of giving a very complex example from one of my projects, I thought I would give maybe 4 examples that we can keep in the back of our heads when we're thinking about program synthesis. So this first idea, okay, is called reprogramming on the fly, right? So we have cities that maybe perhaps has camera nodes all around the city, which send videos to the backend via these Wi-Fi gateways, because Wi-Fi, with these gateways, you have cables, so you can send high quality video feeds in real time. And just in case these Wi-Fi gateways break down, these camera nodes can also be reached by 4G, but this is not a preferable way to send videos. So during a natural disaster, perhaps suppose some of the gateways were destroyed. So the question is, how do we quickly reprogram a camera node stream the critical videos, which has information about some emergency or some problem on the ground, by relaying its video feeds through Wi-Fi connections to other nodes. So here, the camera is not able to send its video feed to the gateway, so it has to rely, but it actually has Wi-Fi connections to other nearby camera nodes. How do you reprogram the nodes to do this? And of course, one way is just to get the software engineer to come in and write up some codes and quickly send it out. But the problem is that rewriting these kinds of codes can be very time consuming and very difficult, and deploying these on the ground is even more difficult. So the second example is more closer to home. So suppose my grandmother wants to start a bakery, and she's really good at cooking, but she's poor with technology. And she likes to make very fresh cakes. So she wants to do just-in-time baking. This means that she will only order the ingredients and arrange deliveries when the customers put in their orders. So she's trying to do all this just-in-time baking without knowing much about technology. And the question is, how can she do this? Maybe through a personal assistant on her phone or something like that, where she could source for ingredients and deliveries in real time, while also selling her own products to the community and getting it out there, getting some kind of reach in advertising her cakes. So of course, she can ask me to write code for her, but suppose she's by herself, how can she actually get a computer or machine to synthesize code to help her with this problem? The third example is a bit convoluted. It's about sorting. So suppose we have the CEO of Acme Books. It wants to design a robot that takes a box of books and arranges them in alphabetical order of the authors on a shelf. Okay, and so he has a manager who buys a generic Android from Atos Bots, and his manager, this manager observes that trivially an empty shelf is sorted. So she has a brilliant idea. So she tells her engineer to just design an algorithm that can insert a new book on a sorted shelf. Okay, that's all she tells the engineer to do. She doesn't tell the engineer to do anything about the Android or the robots. It just tells her, I just need an algorithm to insert a book on a sorted shelf. And then her machine-proof assistant tells her and verifies that this is enough to get the job done. It's able to logically deduce that if you can get an engineer to do that, then everything else is going to work. So this is an example of top-down software synthesis as opposed to bottom-up, where the goal comes from someone at the top and it trickles down to different layers where people work on different sub-goals. And the question is, how can we perhaps automate this kind of a process? And the last example is of knowledge graph queries, and I'm taking this example from Brendan and David's book on applied category theory. So suppose we have this knowledge graph that you see on the right over here, and it shows the entities in the companies, such as Ellen, Ruth, and Chris for the employees, and you have departments like the sales department and IT department. And we also see relationships between them in the form of arrows. So the CEO wants to contact the secretary of Ruth's department. And how can the CEO use this knowledge graph to do that? And suppose we have an external auditor who wants a list of all the managers in the company. And he also wants to check that every manager works in the department they actually manage, right? So these are questions that you could be asking about this knowledge graph. And the question is, how do we get a machine to automatically reason with this knowledge graph and synthesize answers to some of the questions that I've listed here? So all these 4 examples are about program synthesis. It's about different ways a program can be written, either it's for a smart city or for my grandmother or for a knowledge graph or for maybe building a robot to sort books. Okay, so maybe this is where I kind of introduce the general goal here. The goal here is to take a network of agents who could be decentralized, distributed, and to tell this network of agents to accomplish some task. So the question is, how can we get this network of agents to perform decentralized steps? So each of them working on their own thing while managing their own resources, their own embodied resources Each of the agents are going to have different resources, different amounts of computational resources, different amounts of information, access to information. And at the same time, having all of these agents learn how to do their job better by coming up with better and better, more intelligent strategies. So as a machine learning person, when you're looking at a problem like this, the first question that often you'll ask is, what is the action space? Because for a problem like this, action space will be huge, and there's no way you can get anywhere if you have a really big action space. And the second question is, what is the objective function? Is it a function? Is it some energy function? Is it some kind of a distance function? Is there an objective function to all this? And thirdly, how do we incorporate machine reasoning into all of this? Okay, so this is what I mean by decentralized embodied intelligence. We have a network of agents, each of their own resources, and this is the goal of getting these agents to learn to do their jobs better. So with Alphago, some of you may know Alphago was this machine that was designed by DeepMind, and recently this Alphago algorithm was able to beat a world champion in the game of Go. And it was big news in the deep learning community, because for the first time we're seeing that you can teach a deep neural network to explore a very, very big action space and be able to perform at superhuman intelligence levels. Of course, there are criticisms of that, but I'm not going to go into that. The question is, how can we use a framework like this, reinforcement learning framework, and kind of join that with machine reasoning, so we can get agents learning how to make better decisions over time, solving problems better over time. So this is kind of another way of summarizing the goal. The goal is to have neural modules and symbolic modules that work seamlessly together to accomplish some kind of intuitive reasoning, not just symbolic or formal reasoning, but an intuitive kind of reasoning. So in this talk, I'm only going to focus on the symbolic side. I'm not going to talk much about the neural side. That's if you're interested, you can email me or contact me. I can tell you more about that. But we're going to focus on the symbolic side of things. Okay, so this is a category theory talk, but I'm going to be sharing a bit of type theory. I promise that I'm not going to go too far beyond some basic dependent type theory. So I'm going to assume that people know very little about type theory and try to provide a bit of background. So what is a proof assistant, right? So a proof assistant is a software that helps us to prove theorems. It assists us in proving theorems. And in proof assistant, usually we have libraries of axioms or definitions or theorems that we feed into the proof assistant that we use to prove new theorems. And so these definitions of theorems, they make up what we call the global context. So the context is a list of all these theorems and their proofs. And for an example, okay, suppose I have these two definitions in my global context. The first definition is the definition of what it means for a list to be sorted. Okay, so I can say that a list is sorted if it is empty, or it is a one element list, or it is of the form XY concatenated with L, a list L, where the element X and Y are, X is smaller than element Y, and the list YL is itself sorted, right? So we see that the head of the list, which is X, is smaller than the next element Y, and the entire tail of this list YL is also sorted. So this is what it means for a list to be sorted. And on the right over here, you see a way to write that specification in a software called Coq. So this is, it defines some kind of a recursive inductive type in Coq. And then the second definition is that of a function, a recursive function. What does it mean to insert an element I into a list L? So if L is the empty list, then inserting I into L would just be the one element list I. And if L is of the form HT, head and tail, and I is less than the head of that list, then the inserted list will be IHL. And if I is greater than the head, then the inserted list would be H concatenated with the insertion of I into the tail. Okay, so this is a recursive definition of what it means to insert an element into a list. All right. So you notice that this is a very strange way to insert elements in a list. I could always just compose the element, concatenate the element in the front. Why would I have to do this strange thing of inserting I into the tail? And that's because I'm going to prove some properties about this insert function in my next slide. Okay, so I'm interested to prove that the insert function, when applied to a sorted list, gives me another sorted list. So in other words, for all elements A and list L, where L is sorted, then inserting A into L is also going to be, the insert of A into L is going to be sorted as well. Okay, so this is why I define the insert function in such a strange way over here, because I eventually want to prove that this function preserves sortedness. So this is related to example 3, where we looked at the robot that can sort books on a bookshelf. And so here we have what you see on the screen is a screenshot of Cog, and Cog is a proof assistant that will guide us in constructing a proof of this lemma over here. All right, and so on the when we start off this lemma, we're going to see on the right that there's a sub goal, and the sub goal tells us that this is the goal that the human has to solve, and Cog is going to help us in doing that. So the first thing I'm going to tell Cog is to move some of these variables like A, L, and S, okay, where S is the proof that L is sorted, into what we call the local context, right? So these are the local assumptions that I'm making. And so if you look at the previous slide, okay, I have a goal that contains some kind of universal quantification over A natural numbers and list of natural numbers, and proves that L is sorted. And I'm basically moving those quantifications into the local context. And then below the line, we have what is called the conclusion of the sub goal. So I have to prove that conclusion using my local context and my global context. And together, the local context and conclusion is called a sub goal. And it is possible that a goal is a collection of different sub goals. So you can think of this as some kind of a product of all the 3 different sub goals, each of them with their own local contexts, each of them with their own conclusions. So here we see that from this step to the next step, I've told the proof assistant to use to do some kind of induction on S, induction on the proof that L is sorted. So the proof that L is sorted has some additional information in there telling me in what ways L is sorted, and I'm going to use that in my proof of this lemma. So when I do induction, as you can see, if you remember my definition of what it means for a list to be sorted, it has 3 conditions, right? Either the list is empty, or it's 1 element, or it's of this XYL form. So this is why when I apply induction using this inductive type, I'm going to get 3 sub-goals. Okay, so the first sub-goal is to check that the insert of A into an empty list is sorted. The second sub-goal is that insert of A into a 1 element list is sorted. And the third sub-goal is the inductive step. And just to print out all the 3 different sub-goals and their local contexts and their conclusions, I've done them here, and you see them at the bottom right inside the red square. So that's the first sub-goal. This is the second sub-goal. You see that it has an additional x as a natural number in the local context. And the third sub-goal is the induction step, right? We have a lot of different assumptions that we make, such as that the insert of A into YL is sorted. This is called IHS in the context, right? So I don't want to bore you with the details of all this, but the whole idea here is that the proof assistant is helping us to step through the different goals by us telling the proof assistant different tactics for simplifying the goals, right? So the diagram that you could have, before I forget, we also have in the background something called proof term. So while the proof assistant is actually helping us to navigate through these sub-goals, it is also secretly keeping track of the proof of this lemma itself. And at the end of the day, it is going to run this proof term against type engine to check that it actually is a proof of this lemma. So just be aware that the the proof assistant is keeping track of this proof term. So the picture that is kind of useful here is that we have some kind of a category of goals and tactics. The objects are goals. Each of the goals could be a product of sub goals, and we have tactics which convert goals to other goals. So here we see that we started out with our initial goal, the lemma that we are trying to prove, and after we applied induction S, after we applied intros and induction S, we basically get these three different sub goals over here with their own context and conclusions. And I think the thing to keep note in here that sometimes confuses people is that we have to be very careful not to equate types which would normally be equal if we unfolded some definitions from the global context, right? So if I took the insert definition here and unfolded it or replaced it by its definition, they would be the same. They would be equal as types in the type theory, but they are syntactically different. They are syntactically different. Here, we want to make sure that still syntactically, these goals are still different from unfolding, okay, despite being unfolded. And the reason is because unfolding creates problems in unification, which I'll talk about later on. So we really should be thinking about the objects in these goals not as types in the type theory, but actually syntactic objects. And this is where perhaps there's some relationship to weak infinity categories and so on, but I haven't really thought very much about this. Okay, so it's very useful to also consider a related category. It's called the category of types and terms. So this is where we take each of these goals and we kind of map it into the category of types, forgetting all the structure from the goals, the local context, forgetting the fact that these different types have been unfolded with definition. So here we actually want types to be equal. So in this category of types and terms, we have types as objects and we have terms as morphisms. And here you can see that if you have three different types on the right, and we apply a term called sorted ind or induction for the sorted inductive type, we will get the lemma that we're trying to prove. So here you can really think of this picture as a picture of the proof term that's in the background of the proof assistant. And this category is the opposite to the category of goals and types. It's opposite to the category of goals and types. We have the arrows going in the opposite direction. And so the morphisms or the terms in this category can be thought of as string diagrams because we have a monoidal category of types. And so ultimately, for us to have a proof of this theorem or this lemma, what we are actually trying to do is to find a path through these morphisms, through these string diagrams, from the terminal or unit type to the theorem that we're trying to prove. The moment we can find this path, we can say that this theorem is inhabited, and if it's inhabited, then therefore it is true. All right. So the whole goal of the proof assistant is to help us to find this path. The goal of the proof assistant to help us to find this path. So this is where we kind of step outside of mathematics and we think about programming, right? Program synthesis. So in program synthesis, we want to think about intents as types and implementations as terms. So when a programmer is trying to write a program, he has a certain intent. I like to think of the intent as a kind of type, and the actual program that programmer writes will be a term. And so of that type, of that intent. So for example, we could have the type of all sorting algorithms, right? Here, you see that we have this type here, which is a dependent product, right? It takes in L, which is a sequence of natural numbers, and it maps. So in this dependent product, it maps to sigma type, all right, dependent sum. over the list of natural numbers such that this list L0 is sorted, and this L0 is a permutation of the original list L. Okay, so we have used dependent products and dependent types here in specifying the intent of sorting, which is to take a list L and to output a list L0 such that L0 is sorted and L0 is a permutation of L, right? So this is a very formal way of writing down my intent. So if you look at this intent over here, this type over here, it doesn't actually tell us how to sort L, right? So we could have different ways of sorting L. We could use bubble sort, quick sort, insertion sort, merge sort, right? So all these different algorithms would be terms of this type or implementations of this intent. And the way I think about program synthesis, that it is more of a top-down synthesis of the algorithm from the specification, not a bottom-up synthesis. So in usual programming, we start off with writing libraries for functions and then building up more and more complex behavior in our system. But in program synthesis, it is totally possible for someone to start up with a very, very high-level specification and not have any libraries or functions to begin with, and then try to work his way down to an implementation of that very high-level specification or intent. So this is one thing to keep note over here is that the intents, they should really specify constraints on the algorithm, such as the way I'm doing for sort over here, so that we can reuse this type for other problems where they require lists to be sorted. The intent, it is possible in the intent to specify the steps of the algorithm as constraints, but we really shouldn't do that. That creates a very weak kind of a type that cannot be reused. So what we're trying to do here is that we see now that with a lot of software programmers, myself included, we are always looking for implementations on Stack Overflow. We have an intent and we are searching for implementations on Stack Overflow and copying from there. And we're not even sure if the thing that we copied is actually doing what we expect it to do. So what I'm hoping, or what we prefer to be doing, is having machines search for implementations in some library or some kind of a Stack Overflow of its own, using the intents they started out with. So if we come back to the string diagram picture that I had, right? We have these intents, which are objects, and we have morphisms, which are the implementations. And so the goal of the proof assistant, or the goal in program synthesis, is to find a path from the unit type to the intent. So this is, with that string diagram, I drew it that way to perhaps help us to see the analogy with this diagram here of Alphago playing the game of Go, where in this diagram here, the different nodes are different states of the game board, and the different edges that you see here are moves that the game player can take. And so I really do see program synthesis as a form of game like this, where we have goals and morphisms, we have goals and tactics helping us to solve the program synthesis problem. And we could hand off a lot of this tactic selection problem over to a neural network and train a neural network to do that. And that's kind of that's a problem that a lot of people are working on these days in the last 3 years or so. So just to give a few examples of what people are doing in this space, we have people who are looking at using neural networks to prove theorems, and the software like Cockhammer, CockGym, Proverbot, GamePad, and so if you're interested, you can go read up more about that. But they're more focused on mathematical theorems than synthesizing programs. And on the program synthesis side of things, we also have neural networks helping to synthesize software. And here, the well-known ones are like SketchAdapt, Deepcoder, Deepcode, which is not related to Deepcoder, RobustFill, Bayou, GPT-3, for instance, the latest one. They can show that this neural network can actually write code. I think the difference here is that in this side of things, most of the neural networks, they are not actually using any kind of type theory, dependent type theory or proof assistance. they're literally taking natural language input or some kind of a sketch of what the program should do, or a skeleton of what the program should look like, and trying to fill in the details so that it actually works. But there's no verification that the code that you come up with are actually fulfill the intent. So what we are hoping to do is maybe to see a marriage of these two different sides of things in theorem proving and program synthesis. Okay, so I'm going to jump into one of the projects that I'm working with Jingxing Lim, who's in the audience right now. Thank you for coming, Barnaby and Georgios. And so we are going to focus on one of our initial attempts. So the results here are very preliminary, all right? This is one of our initial attempts to apply a proof assistant to doing top-down synthesis of a program. And here's the answer, right? Here's the result here. This very long code that you see on the right. Okay, we started out with the sort spec, okay, that you saw for sorting algorithms. And then we basically threw tactics at the proof assistant to help us to derive a sorting algorithm. And so I'm not going to go into details of all the lines that you see over here. You can maybe peer at it when you want to. But just to summarize, there were some lessons that we learned from this naive implementation of a proof assistant. So first of all, it is very important to use a good library of theorems about what it means for this to be sorted and what it means for something to be a permutation, because throughout this proof, we used many mathematical theorems about permutations, such as the fact that it's reflexive, symmetric, transitive, things like that, right? So having a good library like mathcomp or ssreflect actually helped us a lot. The second is that there is actually a lot of use of a reflection or some kind of a transport to switch between prop and bool. And we also have to use a lot of elaboration or unification to infer implicit and ambiguous arguments. All right, so if that paragraph there just sounds like gibberish, don't worry, I'm going to go into details of what reflection is and what unification is in just a bit. The third lesson that we learned was that many of the goals that you see on the right over here were actually trivial. They were very easy. So if you have a good tactic that could search through some very basic tactics, most of them would just go away automatically. Okay, so this proof is long, but actually most of the steps are pretty automatic. But some of the goals were actually quite non-trivial. So there's one non-trivial step that I wrote in there. It's kind of related to generalizing the sub-goal so that it becomes easier to solve, right? This is one of those weird things where in math, where to solve a hard problem, you solve it by making it harder. You solve it by generalizing and making it harder. So this was a very non-trivial step, at least to me. And so to me here, I see an opportunity to look at what happened over there and to write better tactics so that we can apply those better tactics to other similar issues when we solve other programming problems. Okay, so I do think that this exercise taught us a lot, and that there's definitely a lot of opportunity here for mathematicians to help solve this program synthesis problem. So then now I'm going to talk about this thing called proof as program. So there's this Curry-Howard isomorphism that says that if you have a proof, then that proof is literally a program, right? And we wanted to say, okay, so we finally got the proof assistant to come up with a proof of sort spec, and now how are we going to extract that out into an actual program that does sorting for me? So I'm going to take a step back first. I'm going to start off with something easier, right? So on the left over here, you see that I've defined a sort function, right? A fixed point sort, recursive sort function in Coq. And then I'm going to ask Coq to extract that program out into OCaml, a programming language. And the result is this small program that you see on the right. And what you're going to see is that in the extracted program, it actually tries to define bool and natural numbers and lists from scratch, right? Which is unfortunate because OCaml already has primitives for booleans and natural numbers and lists. So one of the things that you learn over time is that when doing extraction, you have to make sure there's a good mapping between the symbolic objects that you have in Coq with the symbolic objects, with the libraries or the primitives that you have in the programming language, right? And so just kind of keep that in mind for now. So this extraction from proof to program is not as straightforward as we often think it is. So then we did something harder. We took the sort spec that I had earlier, and we just did an extraction to OCaml, and this is the result that you see. You see that this sorting algorithm, it looks really complicated. It looks really long, but if you study most of these functions which are being defined in OCaml, most of them are really just proofs of the correctness of the sorting algorithm. They're not actually useful for sorting at all. All right, and I know that Coq actually tries to remove a lot of these propositions from the extractions, but it really is still quite an issue these days in trying to remove these unnecessary information. It's not an easy problem. Okay, so the better way to deal with these extraction problems is to come up with a language for the implementation that you want. So for instance, if you want to extract your program out to C++, then you should be modeling C++ inside Coq as a type. So you have a type that contains all the expressions or programs that you could actually write in C++. And the reason I call this an implementation theory instead of implementation language is that oftentimes this type will come with certain equalities that says that different kinds of symbolic sequences actually mean the same thing in C++, for instance, right? So a theory is really just a language of equalities. And then what we do after we have this implementation language or this type is that we are going to define a functor to give it semantics. So here, the functor here is called denote, right? And we basically take an expression called E, and we apply denote to that. And denote is going to say that, for instance, plus is going to map to addition, and times is going to map to multiplication within Coq itself. Plus and multiplication being defined for natural numbers in Coq. So we're giving meaning to this implementation theory within our proof assistant. And then lastly, we are going to get the proof assistant to construct a program that writes semantics. So for instance, a better way to write sort spec is that we want to find a program F, expression F, such that for all lists L, there is the application of the semantics of F to L is a list L0 that is sorted and is a permutation of L, right? So if you are able to solve this program, this intent or this specification over here, you literally will have an expression F that you can extract out into a C++ program. Okay, so one of the questions that we get a lot when working on a program synthesis is how this is different from program verification or formal systems, which have been around for a very long time. And I like you. So the answer that I often give is that it is easier to check a solution. For instance, you want to check the factorization of a large integer than to find a solution, to find the factors of a large integer, right? So software synthesis is a lot like that. It's a lot of trying to find a solution rather than verifying that a solution works. And so they are going to require completely different tools and strategies and mindsets, right? So comparing, so for instance, you can think about insertion sort, where you saw both an example of trying to define insertion sort from bottom up by defining the insert function, right? Or we can do it top down by having sort spec, and they look completely different. So in verification, all the layers of the software stack needs to be scrutinized, right? But in synthesis, we often will make assumptions about the semantics of our primitive instructions in our software layer, and then we focus on deriving some new behavior. So synthesis is a lot less stringent in that sense, because we make a lot of assumptions about what the system can do, and then we try to build new software on top of that. So I realized I'm kind of running a little bit behind time, so I'm not going to go into too much detail. So the slides are going to be put online, but so I'll say a real quick about some of the ideas here. So the next thing that you will face when you're trying to do program synthesis is that you need a way of representing the program. And you would think that the right way to represent the program is to use the implementation language that I talked about earlier, but that's not often the case. Sometimes we don't want to do that because that function or that expression that we get from synthesis could be very, very long. Sometimes we might even want to just store the proof script that synthesize that expression, that synthesize that program, instead of storing the actual expression itself. All right. So there are good reasons for doing that sometimes, and I'm gonna leave you to read about that if you're interested. And so I'm gonna focus a little bit more about this idea here. This is my work with Jinsing and Barnaby and Georgios, where we looked at this idea that since we could write programs or implementations, and these implementations could be made opaque, which means hidden or transparent, you realize through the process of synthesizing the programs that we often do not need the implementation of earlier intents or earlier results. We only need its type, right? We only need to know that an algorithm is able to sort a list of numbers. We don't actually need to know how this algorithm does it. And then based on that, we can write our algorithm that builds on top of this sort algorithm. So this actually gives us an opportunity to hide these implementations and put the proof that these implementations do what they are supposed to do on blockchain. All right. So once we have the proof or verification on blockchain, other people can actually look it up, believe that we actually have that algorithm, and then use that to build other software. And when the time comes for them to extract their program, they can give us a certain payment, and then we'll deliver the hidden program, hidden syntax to that engineer or to that problem. And so this can be done by having these smart contracts on top of this blockchain that can kind of move payments and code around, while having the verifications as proof that we have the program that we claim to have, right? And then from these contracts, we can actually create a hierarchy of incentives for people to write software or people to prove conjecture. So for instance, we could have a conjecture about Riemann hypothesis, and we could have a partial proof and put a cost on that, put a cost on applying our partial proof towards Riemann's hypothesis, and then combine that with payments for other facts that we needed in our partial proof. Okay, so so that was blockchain, and I think that in program synthesis, one of the common problems that we also face is the fact that there are many different definitions of the same things. So for instance, when we're writing our sorting algorithm, we have in the library of Coq sorting permutation, we have this definition of permutation in terms of these moves, right? Skip permutations, swap permutations, and transitivity of permutations. But in ssreflect, which is a different library, we have a different definition of permutation equality, and this has to do with counting the number of times an element appears in that list and making sure that the counts match up, right? So we know that these two definitions are equivalent, but using the second one in ssreflect, we're actually able to get our sorting algorithm a lot faster than using the first definition over here. And the question is, if we actually had a specification of intent written in terms of the first definition, how do we translate that into an intent using the second definition? How do we do this transport effectively, which means quickly, right? And then how do we actually make this formal within the type theory itself? More generally, we want to think about equivalent types. When we have two equivalent types, such as the natural numbers, okay, which are unary numbers, and the binary numbers, how do we effectively transport functions like multiplication, addition, or theorems, such as commutativity, from one type to another? So this is a question that there was a study in the paper that I'm citing over here. And there are some possible solutions to this transport problem. We can use Boolean reflection. We can use parametricity, parametric transport. We can use cubical type theory, cubical transport, or we can use univalence or univalent transport. And so here you see that a lot of very interesting math is coming into this program synthesis problem when we're trying to transport between intents. Okay, just to see how this transport is actually at work in our sorting example. All right, so we saw just now we had a sort spec, and if we actually apply the induction principle for lists to that sort spec, we are going to get insertion sort. But if we think of that list as a kind of a binary tree, like if we add some additional structure to that list so that it becomes a binary tree, this means that we actually have to split the list into two sublists, and each of those two sublists into two smaller sublists, and so on. Then we can use the induction principle for binary trees as a tactic, and the result that we get will be a merge sort. Or if you can lift that set or that list to a binary search tree, then you're going to get quick sort, okay, if we apply the induction principle for binary search trees. So here you see that transport is very, very critical for program synthesis. If you're able to transport a problem from one type to another, we can use induction principles, we can use tactics which are otherwise not available to us. Okay, and lastly, all right, I just want to talk a little bit about why you cannot unfold definitions during the trying to prove this in the process of trying to prove the theorem. So for instance, okay, when we have this goal here that we want to prove that for all lists L which are sorted, the insertion of A into L is also sorted. Then to apply induction principle here in this next box over here, you see sorted int. That's how the induction principle for the sorted inductive type looks like. What COP or the proof assistant tries to do is to compare the outcome, okay, which is the last line over here of this theorem, with the goal that we're trying to prove. So it tries to unify the two. It tries to take unknowns, which is question mark P over here. It tries to find a function question mark P such that the goals and the theorem gets unified. They become equal, syntactically equal. And so the solution here, okay, of course, is the function that takes a list and checks if the insertion of A into the list is sorted, right? That's the predicate that we need for question mark P. That solves the unification problem. So here you can see that if we unfold the definition of let's say insert in the goal, then it's possible that no, sorry, this is not a good example here, but sometimes when we unfold a definition, it might be very, very hard for the proof assistant to find a way to unify the goal with a theorem that we're trying to apply. So this is where unfolding can break things. So yeah, so that's kind of like my big kind of summary about program synthesis. The big issues that we need to solve. We need to look at transport. We need to look at unification, and there's a way to kind of decentralize all this using blockchain. And so there's a lot of interesting opportunities for us here for doing some interesting math. So I'm going to now end with this example with knowledge graphs, right? So since David and Brandon, they did a great job talking about applying category theory to databases. And here I want to kind of talk about how we can apply program synthesis to knowledge graphs. So I took this example from David and Brandon's book, right? We have this company with 3 employees and 2 departments, and these are the relationships between them. So in type theory, we can write this as a bunch of inductive types for the employees and the departments. And we can also define functions to map from employees to departments and so on. Okay, so the important thing here is that in a knowledge graph, the query is an intent. The query is a question that we want to solve, and so queries are types. And answers are implementations of that intent. So answers are terms. So we have to really keep that in mind every time we try to design a query for this knowledge graph. So for instance, one of the questions that we had was, who is the secretary of Ruth's department? So here I create a type called RuthSec query, right? It is a kind of a structure or record type or dependent sum in COP. And the answer that I want is called Ruth's secretary, RuthSec. It is an employee, and it has to satisfy these constraints. The constraints is that there is a department of Ruth, such that Ruth department equals the department that Ruth works in, and RuthSec equals the secretary of Ruth department. Right. So this is a bit of a trivial example, but I wanted to show this to show you that a query is a type. And then to find the answer, I can get the proof assistant to do this automatically, right? So I have to derive a term of this type, and I do a bunch of pretty simple tactics. And when I print out the answer at the end, I see that RuthSec is Ellen. Ellen is Ruth's secretary. And together with that, I also have proof that Ellen is Ruth's secretary. So the answer is not just an answer, but it actually comes up with a proof that the answer is what we want. And so in the same way, we want to get a neural network to solve queries on knowledge graphs, because the kinds of queries they can have on knowledge graphs could be very, very complicated. And you definitely do not want to be handcrafting an algorithm for solving each and every one of those queries. So we are now going to kind of step up. So that was an example of an instance of a knowledge graph. And so we want to step up into a meta level now. We want to talk about the schema of that kind of instance that we had earlier on. So this is also from Brandon and David's book, right? We have employees and departments, and we have morphisms from employees to employees. We have morphisms from employee to departments, and called works in, and a morphism secretary from the department to employee. And so this schema here also comes with two equalities, that the department that the secretary works in is the same as the secretary of the department. The department of the secretary of the department is the same as the department, and that the department of the manager of the employee is the same as the department of the employee. Okay, and so here we see that we can actually prove these two equalities based on the information I fed in over here, right? These are theorems that I can prove. And then now what I'm going to do is I'm going to feed that information into a record type or structure. So this record type stores the schema. So you can see in this record type, we have employees, departments, we have morphisms, works in, secretary, manager. We also have two terms, EQ secretary and EQ manager, to talk about the equalities that I mentioned earlier. And then we will say that the instance that we saw earlier with Ruth, Alan, and Chris is an instance of this record type or this schema by providing all the information into constructing this company here. Okay, and the nice thing now is that we could totally work over the schema, right? Now I can throw the instance away. It has all the assumptions that I'm making about my company, and I can now prove theorems completely on top of this structure about all instances of the schema without referring to any instance itself, right? I could prove that the department of the manager of the secretary of the department is the same as the department itself, D itself, okay? And so this gives us a way to kind of work at different hierarchical levels. We could work at the hierarchical, at the level of the instance. We could work at the level of the schemas. We could also move up and talk about the kind of meta or higher order information between schemas, all right? And all this can be done without having to cross those layers, so that someone who works with the knowledge graph instance can then apply theorems that we are deriving at the higher levels, at the meta levels, okay? So this is very similar to what we do with mathematical structures like groups, abelian groups, and so on, all right? So here the example is that, you know, we have this abelian group with all its properties, and then we can define Z, the integers, to be an abelian group, an instance of the abelian group. But there is a problem here now, right? So the problem is that we saw earlier we have this theorem that I defined on top of my schema. But now I actually want to apply this theorem, schema theorem, to the instance of Ruth, Alan, and Chris. But the problem is that the proof assistant doesn't actually know. For instance, if I have a statement about works manager sec in the instance, how would it know that works manager and sec actually are fields of some instance of company, right? Especially if we don't make this explicit to the proof assistant. So this is a problem in unification. So we basically know that the proof assistant needs to find out that there is a company, that instance called $C, such that the works in for that instance is equal to the function works that I had in my instance, right? So you can think of it this way. We actually have the instance of my company, and what I can do is I can have a functor down into sets where I forget all that structure. I forget all the structure. Just think about the sets of employees or the department, and I forget all the other structure. The question now is I need this reverse. We need this other functor to go in the opposite direction, such that we can lift this set without any structure back into the category that has structure. So there are many ways to do this lifting, but to help the proof system, we actually need to provide at least one way of doing that lifting so that the theorems can be applied, right? So this lifting problem is also a problem in unification, and the way that we can actually do this in Coq is to define these canonical lifts or canonical instances. Okay, and I don't want to go into too much detail about this, but the moment we apply some of these canonical information into Coq, we can actually then apply theorems that we have about schemas into instances quite easily, and Coq will do all this automatic work in the background for us to lift the instances, to lift the objects into the right category. Okay, with 1 minute left, I'm also going to talk about another problem that we had with knowledge graphs. So earlier we saw that there is a difference between verification and synthesis, right? In knowledge graphs, we had the same problem. Checking if Ruth is the manager of Alan is different from asking who is the manager of Alan. Or okay, in this case, it's easy, but for instance, you can imagine that we might have to search through all of the knowledge graph to find an object that satisfies the property that we want. So there's this difference between checking something and finding something. So in our work with knowledge graphs, what we did was to make this problem easier by always having some kind of a map between a type and enumerations of that type. So if I have a type of, let's say, siblings of a person T, it doesn't necessarily give me all the siblings of this person T, but I could, for instance, design a function that can return all the siblings, and that's called the enumeration. And having this duality reflection between the type and its enumeration actually helps us in solving many queries. So I won't go into details of that. If you're interested, you can kind of look at my slides a bit more and or maybe email me about it. Okay, so we use this thing called Boolean reflection in solving this problem. Right, so yeah, so I'm just going to also skip this part, which is about how we can work with decentralized knowledge graphs, right? And then where having these inductive types is not practical anymore. So a little bit about that if you're interested. Maybe after the end of this talk, if you're interested, you can ask questions about this. So to conclude, we have I talked a little bit about all the different issues that we have in program synthesis, and I would say that the 4 key areas that we find a lot of work needed is with transport, unification, theory management, and universe management. Theory management is the management of languages, implementation languages. Universe management has to do with managing what all these objects exist in different universes at different hierarchies. And why is this problem of program synthesis very important? Because as we learn from history, information is power, and coding is access to this power. Coding is having access to information, therefore access to power. And what I see in society these days, that a lot of people are stripped of this power because they are unable to code, or they're unable to control the information because of code. So if you think about like social networks out there, or things like the gig economy, where we have all this code that's sharing our information and with advertisers and so on, we cannot control what happens to our information anymore because of code. And so this is why it's important to decentralize or democratize the ability to code, so that we can have a diversity of voices, we can have a diversity of products and services without being controlled by some kind of a huge platform. We have equal access to all the resources and growth, and we can allow people to form communities in this network of code that can support what they want to do, like my grandmother who's doing the bakery and so on. So I'll just end over here with this thing about why it's important to do program synthesis. Thank you.
That's great. Thank you ever so much. That was a really lovely talk. So yes, sorry. So it is a tiny bit over time, but there's no rush. So I mean, if people need to leave, that's obviously fine. But if anyone has any questions, then we can carry on and do a question session. So does anyone have any questions? I will make it so that you can all unmute yourselves. So if you have a question, just feel free to unmute yourself. I see Emily has a question.
Sure, I'll lead off. Thanks very much. That was a great talk. And as somebody with no programming experience, I was able to follow. So I really appreciate it. You mentioned these canonical instances, and the example you gave in abelian groups happens to be the initial object in abelian groups. And I'm wondering if we should think of them in general as initial objects.
Yes. So most of the time, these canonical objects are the initial objects. So maybe I'll just think of an example here. Let's say we think about the category of monoids. And there are two ways of thinking of integers as monoids. We can think of it as an additive monoid or a multiplicative monoid. But somehow we've kind of, a lot of people in the community have made this canonical choice of the additive of thinking of integers as the additive monoid. But there, in some sense, I think so. There's no question. I'm not sure about this. I'm not the expert here, but I'm not sure if there's a question of initiality in here. Sometimes a lot of these canonical choices does not have to do with initiality. I think I could be wrong. Okay. I'm not sure if that helps. Yeah.
Can I ask a question?
Yes, David. Yes.
When you were saying how you said that when you just extract OCaml directly from Coq, it's kind of inefficient and stuff. And so did I understand right that you program somehow C++ into Coq and say you define like all the primitives that you're going to use in your C++ program, and then you prove things about those, or prove that they have analogs in Coq? And can you say more about what that process is?
Yeah, that's a really good question. So that's one way to do it, which is to take the language of C++ with all of its kind of intricacies and complicated syntax, and try to model that accurately in Coq, and then try to prove properties about it, prove it, give semantics to all of those things, and then try to write a program. And from my experience, that doesn't work, because you end up with too many options. You end up with too many. In other words, your action space becomes too big. That you end up too many choices of what the tactics can do in trying to write this program. So what I would suggest often is working with a smaller subset of what I call primitives. These primitives can be mapped out into certain C++ programs eventually when we're done. So what we are literally doing is writing a new programming language that can be compiled into C++. And within this new language, we can then write programs more easily in certain subdomains. And I think that's that's the way to go, rather than trying to model all of, let's say, C++, or model all of Haskell or even Coq itself inside Coq. It just would be too crazy, especially if you have a lot of dependent types going around, dependent sums and products going around too. Higher order languages are even harder to model in the program. But if we have a way of kind of taking out the essential primitives that we need to solve our problem, we could actually do this extraction a lot more easily.
So you take a sub-language of C++ that you're actually going to use, and you implement that inside of Coq, and then you can just prove things with that sub-language inside of Coq, and automatically that will produce a program.
That's right. So you will have to do this final parsing yourself, where you take the expression that you have, which is a tree in the inductive type of the expressions, and then you have to do this parsing where it actually produces the C++ program yourself. I don't think Coq would actually do that for you.
But you could do that once for any program in that sub-language?
Yes, that's right. You can write a parser for that. And so the thing to note here is that I'm sorry, I think I lost the thought. I'll come back later.
Well, thanks.
But that's a good question. That's something that we face a lot in synthesis. Yeah. Oh yes, I remember what I was going to say. So with these primitives or new language that you're designing for the synthesis problem, the question is whether the semantics that I'm giving to it, is it actually verified? Is it actually real? Is it actually correct? Because I could be giving this new language some kind of semantics, like saying, oh, for instance, I have the natural numbers, I have plus and times. I'm going to map it out into the C++ version of adding and multiplication, extracting it out to that. But we know that that's not faithful, because in C++ you get overflows, which means, but the Coq object, the semantics that I'm giving to add and times could be the natural numbers, the unary natural numbers in Coq, which doesn't have overflow problems, right? So there's some kind of assumption sometimes we have to make to simplify the problem, and then just leave the rest of the issues to extraction, and hope that you never get an overflow. So in synthesis, we are okay with that because we're not doing verification. In verification, you have to be careful not to run the overflows. In synthesis, sometimes for the sake of being able to write a program, for the sake of helping someone who doesn't know how to code, these assumptions are useful to make. You're basically going to say that if we put these semantics to a program, this is what will happen, and then we're going to extract it out into C++ code, and maybe learn how to deal with overflows and things like that after that.
Mm-hmm. Cool. Yeah, nice. Thanks.
Okay. And Alan, do you want to unmute yourself, ask your question? Thanks.
Yeah, sure. Thank you so much. That was really interesting. On the subject of what you were just talking about with wanting to solve a problem in some domain and coming up with sort of primitives that are relevant to that class of problems, right? And then sort of manually writing up into C++, say. Do you have any intuition about the class of problems where writing that parser is a lot easier than just solving the problem? Because sometimes, right? Because like sometimes that synthesis step sort of contributes a lot, right? Mm-hmm. And sometimes once you've sort of defined the types, you've effectively sort of almost written the program. And I think like that sort of interplay is really crucial to like practical systems that accomplish these goals, right? Do you have sort of an intuition for where that sort of strategy is more applicable?
That's a really good question that I think about a lot as well. So I would say that if, for instance, I'm kind of working alone in this world on my problem, and I'm not interested in sharing my insights or strategies with other people, and all I care is writing fast code, good code for the little problem that I have, it would be a lot easier to design my own programming language, and then writing my own compiler, and then be done with that. And so because to me, the programming language is a kind of an intent language, and the compiler is literally a proof assistant that is creating an implementation from that intent language. And to some extent, we're saying that there's only one way to design an implementation given the intent in this setup over here. So that will work. That will totally work. And there are some domains where that totally makes sense. Like for instance, if you are trying to design some kind of security for a nuclear power plant or nuclear bomb or something like that, I would say that is the right way to do it. But the question now is if what we're doing is trying to share similar data structures with other people, share similar programming tactics with other people, and building up this whole ecosystem of tactics, strategies, or ecosystems of data structures. Then the little price that we pay in trying to work within a proof assistant with implementation languages and so on could be worth it for the help that we are getting from all these other things that's around us. And so I would say that in this case, what kind of works is if we are working on very generic tasks like writing HTML websites or writing code that accepts payment from a customer so that I can deliver goods to them. These are very generic tasks that a lot of people do, and for that, I think it's better to go through the program synthesis route. And of course, like if I actually design a programming language without a proof assistant and doing all that, I'll have a working system, but maybe tomorrow there's a new payment system that comes out. Maybe PayPal decides to go out of business and that everyone is transacting in Bitcoin, right? I have to rewrite my entire program from scratch. I would literally have to figure out how to do Bitcoin from scratch. And if I had written all my code in a proof assistant, the proof assistant can now try to find an alternative to some of the components which are now broken because PayPal went out of business. So that's kind of my take on this. Hope that answers your question.
Yeah, thanks.
Okay, Lee, do you want to ask?
Yeah, so I typed in my question. So I love this talk. I was wondering if you would care to comment or share any thoughts on the synthesis of control-focused software. I mean, this is a very deep and broad question, hierarchy of control programs, and if this could crack that nut, that would be great.
Can you share a little bit of what you mean by control here? Is it like
well, so for example, in the biological field, it's well recognized that hierarchical control is the underlying principle of biological diversity. What makes one species with 30,000 genes human and with 20,000 genes a worm? It's not the additional 10,000 genes. It's the hierarchical, the control, which is hierarchical. So, but that is one example that, I'm interested in. But, also in the engineering world, which I come from, when you talk about highly complex aircraft control systems and their reliability, it's not just any kind of software, it's control software, which has its own problems and challenges. So I was wondering if you thought about that, are interested in it, have any comments?
Oh, that's a good question. So I haven't thought very much about control, but I just want to maybe I think there are two ways I can kind of answer your question. So the first is actually more from my own research with spiking networks, where we're kind of looking at how neural networks can so-called evolve or learn over time to manage higher order information or more complex thoughts or more complex patterns, and there is some kind of what we call objective function that's involved here, some kind of free energy information that's going on in here that is managing this evolution into something that's more complex and more efficient. And this is kind of related to what you're saying about the biological systems. So what I'm actually working on right now is to find a relationship between that kind of evolution or free energy evolution and type theory. How is it that we could assign a kind of energy or free energy to a certain type system or type theory, and to say that, okay, this one is of a lower energy than another type theory, and so on. So that's something I'm working on right now, and I don't think I can say very much in a short time, but I think yeah, if you're interested, maybe we can talk more offline. It's related to path and the growth and things like that. Then the other way to think about your question is actually something I've been talking to Evan Patterson about, Cat Lab. So we there's a lot of very nice work with structured code spans and using that to model systems, and it's really a very efficient way of maybe designing a good control system. For instance, if you know the relationships and you model them as structured code spans, and you can actually get some verification about the behavior of the system. And this is an example here of thinking of structured code spans as a kind of implementation language. Okay, and allowing us to reason over these structured code spans would be like say reasoning over this implementation language and its semantics, and then writing programs that are then in terms of these structured code spans, right? Would then give us the algorithms we need to maybe fly a plane or something like that, or run a power grid. So I do think that it's very important to do research in these kinds of structures like structured code spans, because they kind of model a smaller set of that type theory where the behavior is much more well understood and well behaved, and we can actually get the better verified behavior. Yes. Sorry, not better verified behavior, but just easier to reason about the behavior of these systems.
Yes, thank you. Thank you.
Thanks.
Okay. Does anybody else have any final questions? No? Wonderful. In that case, I'd like to thank you again, Shaowei. That was a great talk. Thanks for giving it, and thank you everyone for coming along. I will. I'm going to end the live stream now, but I will leave this room open for anybody who wants to stay around and act. So feel free.
Thank you, Tim. Thank you, David. Thank you, Brendan. Thanks, everyone.
Enjoy. Great talk.
Oh, thanks, Brandon.
Yeah, I really enjoyed that.
Yeah, there was a